Hi everyone, my name is Lucas and today I'll be talking about our paper, Probing as Quantifying Inductive Bias. This is joint work with Alexander Immer, Vincent Fortuin, and Ryan Cotterell. Now, contextual representations have led to impressive performance improvements in a wide range of NLP tasks. In turn, this has prompted researchers to probe representations for the information they encode. In our case, we'll be mostly focused on supervised probing, where the goal is to take a model and call the probe and train it to recover some property of interest directly from some words representations. Now, the idea is that if the probe attains high performance in this task, then the representation is said to encode that property. And if the probe does not attain high performance in the task, then the representation is said not to encode that property. Now, there's been a lot of work in probing over the past few years. However, there are still some issues which the community is yet to find consensus on. The first one we term representation selection. And the idea is that some past work would suggest that random representations would encode more information than pre-trained ones. Now, generally speaking, this is counterintuitive, and indeed we wouldn't see why this is the case, since ultimately random representations are fully random. They don't encode any information. So pre-trained informations can only do better than them. So if finding that random representations are better than pre-trained ones is clearly problematic. Now, the second problem we term probe selection, and that basically is, well, what is a good probe? Now, a lot of previous work in probing has opted to use simple probes, and there are some intuitive properties as to why we'd want to use simple probes. However, as shown in this particular example here, this particular representation, in this case, opting for a simple linear probe, as shown on the left, is actually worse than opting for a more complex multi-layer perceptron probe, as shown on the right. That's because the linear probe makes this linear decision boundary linear separability assumption in terms of how the classes are structured, how the information is structured in the representation space, and that doesn't hold. What that is to say is that always opting for a simple probe is clearly not a correct solution. And indeed, there has been a lot of work in this that is particularly trying to address this question, and there's more sophisticated methods. Indeed, a lot of recent works attempt to trade off probe performance and complexity and try to ameliorate this problem. That is to say, this is still an issue that needs to be kept in mind. The third problem we highlight is task selection. And this is divided into two subproblems. The first is, what is the boundary between probing tasks and NLP tasks? Well, initially, in a lot of probing work, tends to focus on tasks that would seem simple. However, more and more other tasks are considered, and indeed, some work has also called for the use of the exploration of more complex probing tasks, which begs the question, what exactly differentiates probing tasks from NLP tasks? And if there is a difference between the two, then where does that boundary lie? The second subproblem is, how should probing results be interpreted? After all, we've run all these studies, we've gotten all these results, but ultimately, is there some way that we can use them to help us obtain further insights into how to improve models for downstream tasks? Now, with all this in mind, the main focus and the main contribution of our paper is to present a framework that attempts to, a unified framework for solving all these problems simultaneously. And the key idea is that we argue that the purpose of probing should be to quantify the inductive bias that representations provide for particular tasks. And in terms of how to achieve that, we propose to do it using the Bayesian evidence. Now, the Bayesian evidence has a lot of properties that would seem suitable for, in light of the previous problems that were mentioned. In particular, it has an Occam's razor-like effect. So we would expect, at least in principle, that it would prefer pre-trained representations over random ones in terms of selecting between the two, and if we use it to compare different probes, then we would find, or we should find, that it should prefer probes that are just right in terms of complexity, as opposed to probes that are too simple or too complex. Now, we want to do this. Fine. Okay. How do we actually do it? How do we actually achieve this? Well, we'll start formalizing this idea a bit more. We're interested in computing the evidence, and in practice, what we'll be doing is computing the evidence of representation probe pairs. So, as the name suggests, a representation probe pair is just a pair of a representation function, like BERT, and a probe specification P. And this is basically a prior over a family of probes. Now, this may seem a bit different from what people usually do, but in practice, this is very much connected to what is already done. When you're training a probe, using a particular setting of the architecture, and also, say, L2 regularization with a particular weight on that regularization term, then there is a connection to that, and using a Gaussian prior on, or putting a Gaussian prior on the weights of a neural network. So there's a close connection between the two. That is to say, this is not that different from what people are already doing. However, I'll highlight in a second where the difference comes in. But anyway, these representation probe pairs will come from a set of representations, which are the ones that we want to compare, and also a probe family, which generally speaking is just a set of all different priors we want to consider. Now, the difference is that where this is all leading to is that, as we said, we want to compare representations in terms of the inductive bias they provide to a task. And we would like to sort of try to make this independent of the choice of probe. So what we'll do is that for every representation, we'll be interested in finding the probe such that the evidence is maximized. And then we'll be comparing representations using those optimal probes, so the optimal probe for every representation. What this means is that the optimal, and I mean, this also makes sense, right? There's no reason to think that the probe that is best suited for BERT would also be the one that is best suited for fastText. Maybe fastText only needs a linear probe, whereas BERT would prefer to have more layers because it encodes things more non-linearly, just as an example. But the point is that this would allow us to be able to make more fair comparisons. Okay, so that's the idea. We'll be computing the evidence for representation probe pairs. So how do we actually go about computing the evidence? So there's far more details about this on the paper, but I'll just give the high-level idea. First, in order to actually be able to talk about the evidence, we need to introduce a probabilistic model. So specifically, we're going to go over the generative model for this. And again, without going into many details, the idea is that we have some input sequence, and then we can put that through BERT to obtain representations for every word, or every subtoken to be more precise. And just generally speaking, we will allow these to be stochastic, even though in practice they're not. So again, in this case, if R is BERT, then they wouldn't be stochastic. It would be just completely a non-random, deterministic representations. So that's the representation portion of our representation probe pair. Then we'll have our probe, unsurprisingly. And again, this would be stochastic. And you can see that that's where our probe specification also factors in. And ultimately, what a probe yields is some random vector, which you can think of as logits, which in turn can be used, you can think of parameterizing a categorical, which gives us a distribution over the, say, part of speech tags that we're predicting. But more generally, it can just go into some likelihood. The point is, or the most important thing here, is just that all we need to do to be able to get the evidence is just make sure that we formalize probing from a probabilistic standpoint, and that's all we're doing here. And the paper has more details on how we do that. But ultimately, it's just reinterpreting both representations and these intermediate outputs of probes as stochastic, or possibly stochastic. Anyway, the model before implies the following joint distribution over the data, and in turn, we can obtain the evidence by integrating away the representations H and the intermediate values output by our probe F. So, since our representations are usually deterministic, as I mentioned, we can actually further simplify this. And ultimately, and this is what we're really interested in, we define the inductive bias of our representation in the following way. So it's basically just the evidence where we've maximized over our whole probe family. So when we're comparing different representations, we'll be comparing them according to potentially different probes or different probe specifications for every representation, which allows us to compare things a bit more fairly. And this can be done efficiently using the approach in Immer et al. Okay, so in terms of experiments, we have two sets of experiments. The first are some multilingual tasks from universal dependencies, mostly focusing on BERT and fastText. These tasks are mostly morphosyntactic tagging tasks, but we also consider some dependency arc labeling tasks. In both cases, we consider 6 typologically diverse languages. The second set of tasks are some English sentence level tasks. We have a larger set of representations in this case, and 4 particular tasks shown there. So I'll highlight a few of the more important findings. The first is that our approach seems to indeed solve the problems that I mentioned initially. So, for example, random representations are always, there are worse inductive bias for the tasks we consider than the pre-trained representations. And also we find that the optimal probes for every single representation, for every representation and task, well, they do depend on the representation and the task. So that suggests that indeed we do want to perform this maximization that we're introducing over the probe family. Another interesting finding is that fastText appears to be a better inductive bias than BERT in some tasks, and we think that, for example, this is the case for Turkish, which we believe it may be because of its agglutinative nature. And also, finally, we find that if we expand our probe family to allow for per parameter regularization, so we effectively allow our probes to be less than linear, we find that optimal probes may be sometimes less than linear, which would suggest that indeed this idea of relying on linear probes because of their simplicity may be insufficient, in that we can actually find even simpler probes, less than linear probes, that would seem to be better suited for some representations and tasks. So yeah, thank you for listening.